let's get the logistic first, and then we can start to introduce a little bit of this class, and then let's see what we can do here. Okay. So first is that since you guys already logged in here, so this is the Zoom link, okay, for this class. And then if you have things to do during the class hour and then you miss a class, that's perfectly fine. So the next morning, the class recording will be uploaded to YouTube. Okay, but then keep in mind that the YouTube recording, the quality might not be that high. The reason is that I'm right now in my living room and then talking to a camera. Okay, so that you really can't expect the teaching quality to be as good as the in classroom situation. Okay, but then the YouTube video will be there, and then you will be able to watch the replay. And then, of course, if any of you will want to have an objection, okay, of posting the video, then please let me know. And then in that video, in the video that we post on YouTube, none of your name or your voice will be recorded. Okay. And second is about the grade. Okay. Homework will be 60%, and then midterm and final will be 20% each. Okay, will be 20% each. So 1 second. Yeah, it's a little bit messy here because I just changed my recording setup this morning because my recording studio was in the basement, but then it was really cold because of snow. So I have to move it upstairs. Okay, so homework 60%, midterm and final 20%. And then I was thinking, like, if some of you want to volunteer to do a course-related project, okay, you can kind of waive this. We had it in the first year, and then 2 students from physics department, but they're very senior. They're like in their 4th year in PhD. They took the project, okay, and then that went okay, and so I think we can discuss that after midterm, okay, just to see how things evolve. And then the policy is very flexible. Let's say for grad students who usually prefer not to do homework, okay, you can waive this. Okay, you can waive this. And once you waive this, and your grade will be decided by midterm and final, right? Completely by the midterm and final. For example, you don't turn in any homework, then your midterm will be 50%, your final will be 50%. Okay? If you turn in half of the homework, then your midterm and final will be raised to 35% and 35%. Okay? So it's all proportional. So for some homework, you can option out. Okay? And you actually don't have to email me. Just at the end of the semester, I count the number of homework that you guys submitted, and then I do the math here. Okay. And for undergrad, I would strongly suggest to do homework in the first, do the first few sets of homework just to have a sense of what it feels like, and then and then after that, it depends. Okay, it depends. And for the grade, since we only have 3 students, so we're not going to do any like normal distribution, right? It's impossible. So what I would do is I would compare your score to previous years, okay, previous 2 years, and then assign a letter grade. And from what I've seen, it's fairly easy. Okay, I remember the first year. I think you can get B+ if you're 30 points, okay, out of 100. And then you get A- if you're 60 out of 100. And of course, I wish some of you can score 100 because usually someone scores 100, okay? And then textbook. Any questions about grade? Okay. Textbook. The recommended textbook has been posted on the syllabus. usually, okay, we don't need textbook because I will post all the off my notes. Okay, whatever I have in my hand, you have that on your computer, so you don't need to take notes. And then if you want to use a textbook, then the one that I would recommend is Quantum Electronics. Okay, by Yarif. Okay, so he's a distinguished professor at Caltech. I think he's almost 90 years old now. He's actually my advisor's advisor. Okay, and then he also taught my quantum electronics. And then another professor here at UVA, Bobby Wyckoff, also learned quantum electronics from Yarif. Okay, but we are kind of like 20 years apart. Okay, so this is an excellent book. Let's see, what else do we have here? Oh, and office hour. Since we only have 3 of us here, so I think we don't need an office hour. So if you have any questions, you can just ask in class, okay? Or let's say if we finish the class a little bit early, then you can ask after class. Right? I don't see a need to schedule a separate office hour. Okay? Any questions about this class? Okay, no? Good. Now let's get started. So all this information, you can find it in the syllabus, on the syllabus, so I will just erase it. Okay, now let's get started. So the class, the actual name should be quantum electronics. Okay, there's no optical there. Quantum electronics itself is a subject to study light and matter interaction. The reason usually people add optical in front is because to make sure that no electronic people, okay, accidentally enroll in this class, because it looks like we're talking about some electronic device that behave in a quantum way, but actually that's not the case. And in this class, what we're going to study, okay, fundamentally, is light and matter interaction. Okay, light and matter interaction. So, for example, you can have one very probably popular example, all of you should have known this, is that if you shine light, for example, into glass or into water, right, the speed of the light will change. It will actually become slower. Okay, and if you shine into, for example, most of the metal, right, the light will actually be reflected. And I think we are all very familiar with this, but rarely textbooks tell you why, right? And also there are many different other light and matter interaction, and those are actually discovered very recently in the past 50 to 70 years. And those are only possible because we now have lasers. Right? Lasers are very intense, directional, and coherent light that enable people, okay, to see the type of interaction, okay, that you can never see before. So if we kind of look into, okay, what this light and matter interaction really mean, okay, we have to kind of answer some fundamental questions. The first is, okay, what is light? Right, what is light? And the answer is kind of in a 3 different levels. The first is that, of course, if you learned EM wave or any similar class, then you know that the light is just oscillating electromagnetic field, right? And it obeys Maxwell's equation. Okay, so of course in this class, okay, later today I will review Maxwell's equation, and so that we can use it later in this class. So that's kind of the answer in a classical level. Okay, Maxwell's equation, determine the behavior of the light. And then the next level would be kind of the is the quantum level, right? In quantum mechanics, you can quantize light, and then to get a concept, okay, photon, right? Photon is say Maxwell equation, and here is quantum, and then you get photon. Okay, and these two are actually the foundations to study light and matter interaction, right? If you can't write down the mathematical form of light, okay, there's no way you can understand how it interacts with matter. Right, so in this class, we're actually, in the middle of this class, we'll show you, okay, how you can transist, right, from Maxwell equation to quantization of light, okay, quantization of light. And this is about the light part, and then what about the matter, right? Matter, so regarding this, okay, there are three different levels. Okay, one is that you can treat it as classical model. Or simplified model. What I mean here is that when you look at matter, okay, you don't try to understand the inner structure of it. Right, inner structure is actually a lot of atoms, and then each atom have its energy level, and then it behave in a quantum mechanical way. You don't try to dig into that. Instead, what you do is say, okay, if I probe the matter, then I can measure some parameters of that matter. Right? For example, Young's module is a parameter for most materials. Refraction index is also parameters, right? So there are many of these parameters. You don't have to understand why this matter produce these specific parameters. All you need is to know that, okay, somebody can measure this for me, or I can measure this in this way, and then once I get this number, I can use it, okay, to plug into a classical equation and then to solve light and matter interaction, okay? And this is on the level that looks a little bit kind of overly simplified, but then 99% of the research is done in this way because, like, you just need a number, right? And then the next level, okay, when this combined with Maxwell equation, then we say this is a classical model because your light is classic, your matter is classic. And then we can have, the next one we can have is something called a semi-classical model. Let's see. Semi-classical model, probably quantized. So what you can do is that you can quantize your matter. Right? It's like an atom with two energy level, right? That's the simplest case. Or you can do a more complicated atom or even crystallized structure. But the key concept here, what we call a semi-classical model, is that you treat your matter as a quantum object, for example, a two energy level atom, and then you treat your light as a classical light, right? Maxwell equation. And then later you will see the reason for this is that when your light is a strong laser, you can see that even you quantize, okay, your field, actually these two are approximately the same, right? So if the light intensity is very strong, then you have a lot of photon, then you kind of approximate to the classical light or coherent light, okay? And then finally we'll have a full quantum picture, which you will have an atom that's quantized, and then it will interact with individual photon. Okay, so in here we will actually give you guys an example, a model that a single photon interact with a single atom. Okay, and that's actually something looks very elegant and simple in theory, and it actually took scientists many years to actually do it in the experiment. And I think there are 2 Nobel Prizes, okay, awarded for this, okay, just to the ability to control single atom and single photon and let them interact in a quantum mechanical way, okay. And so these are the kind of the fundamental level, okay, of what we need to understand in light and matter interaction. And then there's a more practical reason why we look into this, right? Because we're actually in engineering school, we're not in physics. The reason that we study this light and matter interaction is that you can actually draw, well, a lot of the real-world applications are actually based on this, based on light and matter interaction. First, a very famous example is laser. Let's say applications. So we'll learn a little bit about lasers. This subject is kind of duplicate with Professor Joe Campbell's class, laser and optics. But I think it's fine. We just probably spend 1 week on this. Lasers are super useful. And then if you have an iPhone, you actually have many laser arrays on your Face ID. What they do is that they emit the near infrared light from a vertical emitted laser diode, which is very popular now, and then the light illuminate your face and then reflect, and then there's a near infrared detector there so that you can kind of scan your 3D structure. So this way you can use a photo to fool the Face ID. And then much earlier, if you ever have, probably you guys don't own a CD player. CD player actually have light shining onto the CD and then read out the information. And lucky for you guys, you never have to use it. And then the second one is something called nonlinear optics. So what nonlinear optics is that it's basically anything that's not linear is called nonlinear. Linear means that you have an input, you have an output. If you increase your input intensity by twice, your output intensity will also raise by twice. That's a linear relationship between input and output. And nonlinear simply means anything that violates that. A very simple and non-meaningful example is that if you ever play with magnifying glass when you're young, if you're still playing with it, that's kind of odd. So what you can do is that you can focus the sunlight and then put it in front of a piece of paper, right? And then what that would do is that it will focus the light and then burn your paper. Now think about it, right? That's not a linear process, because there's a certain threshold beyond the sunlight. Once it reaches certain intensity, that the paper will be burned, and then your light can transmit through, right? So if you look at the transmission versus this is the output, this is the input, you'll see that at the beginning there's almost nothing. It's linear. And then if you reach certain threshold, it gets burned and then it goes out, right? So that's a nonlinear process, but it's kind of meaningless because that's an irreversible process, right? Once you burn the paper, it's done. We actually look at a lot of nonlinear optic process that's way more interesting. For example, you can create, you can input, for example, you can input a red laser, and then the crystal will actually output a blue laser, right? It will change the laser's color, and then also you can input a continuous wave laser that's steady in time domain, and then the output would be a femtosecond ultrafast laser pulse, right? So there are all kinds of ways that you can convert your input to an output. And then the best example, maybe most of you actually have used it in the past, is that if you ever buy a laser pointer, right, there are usually two colors you can choose. One is a red one, that's a boring one. The other is a green one, And the green one actually has a nonlinear crystal inside. So what it does is that it's difficult to build a green laser. So what people do is that green laser is at 500 nanometer wavelength. It's green. So what people do is that they have an input at 1000 nanometer. It's in the near infrared. At this wavelength, the laser is extremely easy to build, and then it's very high power, and then also very cheap. So what they do is that they build this laser, and then they put a little bit of crystal in front of that laser so that the frequency gets doubled. okay, and then the wavelength, get to the half, and then it become green light. And so when you buy a green laser, okay, something you shouldn't do is to save too much money, right? Because some manufacturer, okay, if they're not being very good, what they would do is that they will not block the initial high power laser. Okay, so what's coming out is green laser and then the initial pump laser. And then this one you can't see, but then you can get damaged by it, right? So, for green laser, usually spend a little bit more money, and then, option for the light that's not really high power, because our eyes are actually very sensitive to green light. As a matter of fact, our eyes are actually way more sensitive to green light than a lot of the commercial photodiode. If you actually buy a photodiode and try to detect green light, you will actually see it first by your eye, and then the detector will respond. Okay, so it's kind of an interesting fact. And then nonlinear optics, okay, and then later we'll talk a little bit about how we can use this for telecommunication, right? That's the backbone of internet. And then we will touch a little bit about the quantum side, okay, like quantum information, quantum computing, but that's really not the focus, okay, of this class. So it's really laser, nonlinear optics, and then a little bit of quantum optics. And whenever we talk about this, we'll introduce an application together with the physics together, okay? And since we only have 3 people here, so if you ever come across something that's interesting, okay, you think it's interesting, you can just send me an email, and then we can talk about it in the class, okay? And then, for example, if you're interested in how to do the it's called LASIK, the eye surgery, where you treat near sight, right? You shine lasers in there, and then change the structure of your eye, and then there are quite of interesting things that people do with the nonlinear optics. Okay. If you don't have questions, then we can start with the very first thing, okay, review what is light, right? Maxwell equation. And I'll first write it down here. Let's see. Okay, Maxwell equation. I don't know which version you guys learned in the past, like integration or differential, or just, there are other ways to write it down, this equations, but in this class or in any when you deal with light, usually you write the differential form, and then we'll talk about them one by one here. Okay, we'll talk about them one by one here. So Maxwell equation. Maxwell equation, the most part of it is actually a summarize of what people see in the experiment. Okay, so the first one is Gaussian law, which is actually the same as Coulomb's law, right? The second one is magnetic Gaussian law. Okay, the third one is the Faraday induction law, and then the fourth one, okay, without the last part, is actually the Ampère law. And then Maxwell's contribution, okay, to this is that first he add a term, okay, in the Ampère law, and then the second one is that he's really good at mathematics. Okay, a lot of the experimentalists in the past, they don't. Well, for example, Faraday, I think he didn't know calculus, right? He had no idea of what calculus is. So when he saw, Maxwell rewrite his equations, okay, he's actually a little bit mad, okay, because he couldn't use it, okay. So and Maxwell's contribution is to write them in differential and write them in integration form, so that you can actually put this equation together and then derive the EM wave, right, electromagnetic wave. So the EM wave, okay, come from these two equations with this term. EM wave was first derived by Maxwell, okay, and then the experiment was done by Hertz, right? And then also a kind of accident is that when Maxwell derived EM wave, he also found that the wave, the speed of the wave is the same as speed of the light, right? So that include, okay, that's kind of explained why light is part of the EM wave, okay, because it follows agree with the experiment on most levels, and then the first evidence is that the speed of light is the same as speed of the EM wave, okay. Now let's study them one by one, okay, very briefly. So the first is the Gaussian law. The Gaussian law, probably the way that you, the form that you are more familiar with is this. Electrical field, okay, the divergence of the electrical field equals to rho, okay. Sometimes you write it in this way, or sometimes you write it in rho free electron divided by epsilon r, right? Relative permittivity, okay. And here the definition of divergence is, okay, is that this is a vector operator okay, and then dot product with your electrical field, which is also a vector. Okay, mathematically, this is what it looks like, and then rho is the charge density. Okay, charge density, and so this Gaussian law actually comes from a much simpler equation, okay, which is the Coulomb's law. Okay, Coulomb's law, we probably all learned it in high school. Okay, you have two charge A and B. Their distance is r. Okay, and then the force that, for example, the force that because of the charge A, okay, the force that B experiences can be written down as the charge of A times the charge of B, okay, 4 pi epsilon, and then the distance square, okay. And then here you notice that, okay, the force actually it's a vector, right? Force actually has a direction. The direction is, pointing from, extension of the line between A and B, right? So sometimes, okay, people write it down as r, okay, points a direction, okay, r direction, and then divided by its magnitude to the third, right? So the amplitude cancel each other, so eventually it will be 1 over r squared, right? And then this gives you the direction. Or, okay, if you prefer, you can write it down in this way: qa, qb, 4 pi epsilon, er. E usually means a unit, okay, unit direction. Unit pointing towards r, okay, r direction. So the unit is 1 here, and then r squared, right? R squared is the distance, okay? It's just a number, it's not a vector. So this way, you're kind of pointing the direction and also tell you it's 1 over r squared, okay? This is the Coulomb's law. The Coulomb's law was, discovered by experiment, right? So Coulomb designed a very nice experiment that I kind of forget how he actually did it, but then he used a mechanical way, okay, to amplify the very small change between two charges, okay, and then kind of project it on a very large mechanical projector so that he can measure, okay, very small change, okay, between the distance of A and B, okay. And so it's experimental observation, and if you have to ask why, I honestly don't know, okay, but there's many ways that you can kind of interpret it, but none of them make any real difference, right? You can say that, okay, the R square law means that Gaussian law is possible, and then because of Gaussian law, then you can have Maxwell equation, and you can have light. But then the question is, there could also be a universe where there's no light, right? So you can kind of rule out that possibility, so that the whole argument is actually pointless, okay? So right now, okay, because the R square law is linked with this, later we'll show you why, and also linked with speed of light and everything. So there are actually a lot of people trying to measure this factor here. If we say x factor, right? They want to measure, is it really 2? Or is it 2 and then many 0, and then there's some number here, right? So they're trying to do this measurement, and then right now I think, okay, it's either 10th digit or 30th digit, right? So it's still all 0. So there's no evidence saying that it's not 2. Okay, there's no evidence saying it's not 2. So you can safely use it. And now let's take a quick look of how to convert the Coulomb's law into the Gaussian's law, right? And the idea is actually very simple. Whenever you see something, okay, let's say I is proportional to 1 over r squared, okay, you know that there's a conservation law here, right? For example, the easiest example is that if you have a light bulb, right, it's emitting like evenly around the space, and then the question is, if I measure here and I measure here, okay, what would be the light intensity difference, right? And the distance here, let's say r, right? Or how the light intensity change with the distance. And we kind of all know, right, because of energy conservation, right? When the light propagates to here and the light propagates to there, right, this larger circle, the total amount of energy is the same, right? The total amount of energy is the same. So that you can see, okay, if you draw this as a sphere, then you say this is intensity. Intensity means the power over unit area, okay? So your intensity at r times your area, 4 pi r squared, has to be a number, constant number, right, because of energy conservation. And therefore, your intensity of light, okay, goes 1 over r squared, right? 1 over r squared. That's, if you don't believe it, you can kind of do the experiment by yourself, okay? But make sure that your light bulb actually is not a laser, right? Because laser is directional, right? So even at a large distance, you still receive the same power, okay? And yeah, this is actually, interestingly, this is a way that, I don't know if you guys know how scientists know the distance between the Earth and the stars, okay? How you actually measure it. The answer is, okay, when you look at a star, the first thing you see, well, two first things you see. One is its color, right? For example, the sun is kind of white, but also a little bit glowing red. And then there are other stars that are way more like into the blue, and some are into the red, right? You can actually measure the color very accurately. Okay, and then by using quantum mechanics and general relativity, you can actually see. Okay, you can actually use the color to determine the size of the star. Okay, there's actually a strong one-to-one correlation. For example, if there's a star that's emitting exactly the same light spectrum as our sun, okay, then it actually will, the size of it will actually be the same as our sun. Okay, so and knowing this, then what you can do is that you can use the color to get its illumination. Let's call it brightness. Well, yeah, let's call it brightness. Okay, so for example, the sun, okay, we know how much energy it will emit, right? Because we can know from its color, know its size, and then know how much energy it illuminates. But then when you actually look at the sun, let's say, well, there's a star that looks exactly like the sun in the sky, but then the intensity is different, right? When you look at it, it's actually darker than you thought. Then why, right? The only possible way is that it's so far away, right? Because the light intensity, okay, you can see on Earth, from a star, if it's the same star, if you double the distance, the light intensity will drop, okay, 4 times. Okay, so this is a way actually, you can use the light intensity and the color. I don't like the brightness. Maybe, yeah, I actually don't know how they call it. I just know how they do it. Okay, so let's say color and brightness. Okay. So you use these two information, you get the mass, you get the illumination power, and then you combine with this, and then it gives you the distance from the Earth. Okay, and then later, okay, people discovered that you will see, okay, what is there a second check, okay, of this thing, right? Because it looks a little bit risky to based on your to draw a conclusion from something that heavily calculated, right? And then there, what the physicist does, or what the astronomers they do, is that they actually calculate a lot of stuff, and then they all agree with each other. So that's kind of means that it's self-consistent, okay? But it doesn't mean that it couldn't be wrong. Okay, it doesn't mean that, because like in the past we have seen a lot of times that because limited by the way that we can do experiment or we can do the observation, that you only receive piece of the information, and then the theory, okay, although it explains all this, but in the future, okay, if you can see more, or if you can measure more, you add more information, and all of a sudden you see, okay, previously it was wrong. And in a mathematical way, you can kind of understand this as, right? You guys all do this, is to find the minimum of a function, right? If you start from here, all the information you receive is from here, then you would think this point is a minimum, right? But once someone put you two further information, you see, oh, there's another minimum, right? So whether our theory is a local minimum or really a global minimum would change, okay, with the perspective of time and with the technology level, okay. Now let's go back to the Gaussian's law. So what you will see from here is that similarly, if you have a charge, and then you know that, okay, now the force or the electrical field is 1 over r squared, which is similar to the intensity of light, okay, from a glowing ball, then you can see that then there should be a conservation law here, right? When you integrate over the entire sphere. What Gaussian did, okay, back then, what Gaussian did is that he looked at it and say, okay, actually, you don't need to do it over a sphere. You can do it for any surface. And what you will get is that, for example, if there is a surface here, and I want to integrate over the entire surface, right? Sum the intensity over the entire surface, not just the sphere. Then what you can do is that you can use the principle of calculus, right? Divide the surface into many, many smaller pieces. Okay, many, many smaller pieces. And then for each pieces, let's say there's an angle, right? A unit angle. So you know that, okay, if there's a unit angle and then there's a radius, then the surface area here, right, surface area here depends on the distance from the center to your surface, right? If it's wider than a certain angle, it will spread out more, right? So this unit here can describe as E, electrical field, times unit surface, okay, unit surface. And the unit surface, the electrical field is proportional to 1 over r squared, right? 1 over r squared. And then the unit surface, okay, unit surface is r squared, okay, let's say d theta. Right? So unit surface actually is a square law with your distance. So what you can expect is that, okay, these two will cancel each other. And then when you do integration of the entire thing, what you get is just integration of the angle. Right? It's a three-dimensional angle. That's what you get. And we know that in two-dimensional, okay, when you integrate over one round, you get 2 pi. Right? In a 3D, okay, 3D coordinate, when you integrate over the entire space, what you get is 4 pi. And then you can actually, if you're interested in y, okay, you can go to Wikipedia and search for sphere coordinate, okay, and then it will show you, okay, how you can change, how you get this d theta and then y, okay, there's a 2 there. And the answer is there's a integration of cosine. Okay. So what we get, okay, from here is that, so basically this is just a review. Okay, so I'm not going to derive this in detail since I'm assuming that most of you already know this. So what we will get is that you have integration over the entire surface, okay, about your electrical field multiply with your unit area, and you can understand this as some kind of conservation of your electrical field. It will equal to the charge, okay, divided by 4 pi epsilon. Okay, these R2 cancel each other, and then there's an integration over d theta d phi. Okay. Okay, the three-dimensional angle. And then we know the result here is 4 pi. Okay, so eventually you get Q over epsilon. Okay, Q over epsilon. And you can see here is that because in this derivation, right, the location of the Q actually doesn't matter. You can put it anywhere, right? So what you can do is that, okay, if you have many charge here, then each of them would generate electrical field, and then each of them carries a charge, and then you can sum the electrical field together on the left and sum the charge on the right, right? So eventually this would be like this. The electrical field, again, doing this, and then on the right-hand side you have epsilon 0. Okay, sum all the charge inside, okay, this area, right? And then they all contribute to this, okay? So this is the integration form of the Gaussian's law, okay? Any questions here? Okay. And now, this integration form can be changed into this Gaussian's law through divergence theorem, or somebody call it Gaussian theorem, Gaussian law. And the way to look at it is kind of interesting. Okay, if you look at the left-hand side and you look at this picture, it looks like something wants to go out, okay, of this box, right, of this area, and then you're summing up all of them, okay. How many of them are going out at a certain time, right? So let's say if I draw a box here, let's don't think about it as electrical field because that's kind of difficult to picture it. Let's think about it as water, right? Water or air, okay? Let's say they're going out, okay, from this box from all the direction, right? And then from all the direction, and let's say the speed of the water is f, right? And then how many it goes out in a per unit time is times your ds, right? That's in a small space. Okay, there are so many waters going out. And what does that tell you? If waters are, and if you do an integration of this, what do you think you will get? Let's say if you do this integration in a water pipe, right? Water flowing from left to right, and then you draw a box and then you do this integration over all surface. You probably will get 0, right? Because water are flowing in from left and going out from right, right? So that this being 0, okay, simply means that there's a conservation law of the water, that the amount of water inside this box is not changing, and what that means is that your water cannot compress, right? Your water's density is the same. So this is actually something that you can, if you ever go into fluid mechanics, okay, people will tell you, okay, this is the first law that you should think about, whether a fluid is compressible or not, right? Now, if this is not 0, then what does that tell you? Let's say it's larger than 0. Okay, if it's larger than 0. If it's larger than 0, what it tells you is that there's a source inside. Right? There must be a source inside that somehow create water from nowhere. Okay, and then spreading it out. Okay, so Gaussian look at this and think, okay, this is very interesting, and then he derived a mathematical equation to describe this. Is that okay? If you do this integration, calculate how much water going out. If it's not 0, that means there must be a source inside. And then if there's a source, then kind of the source, if there's a water source, then the source of course has some relationship with the with your velocity field, right? You have to generate the water. So if you do, and then he find out this, okay. Okay, the divergence of this. Divergence of your velocity field actually tells you if there's a source inside or not. Okay, and this is very interesting. It's hard to explain, okay, intuitively, but one thing you can kind of remember, one thing you can kind of see is that, for example, for magnetic field or for electrical field or for any water field, if it goes in a loop, if it goes in a loop, right, that's conservation law, right? Water from left goes to right and then coming back and back. And if you draw any field that looks like this, and then you calculate the divergence, it's always 0. Okay, it's always 0. So divergence is not 0, meaning that there's a source here, something coming out. Okay, something coming out. It's a divergence. Okay, and it's the source point. Okay, that's where it's not 0. Okay. Sorry, yeah. It's whenever you have a source, and then you will have this relationship, not just a source point, okay? Not just a source point. Wait, take that back, the source point, yeah, because of here. Okay, then, so if you look at this, okay, and it what it does is that it takes the integration of a surface into an integration of the body. Right, surface integration into body integration. And then if you look at the integration of the Coulomb's law, right, on the right-hand side, it's actually a body integration. Right, it's actually a body integration. I think here it should be rho. The charge density times the unit volume, and then you integrate that, that gives you the total charge. Okay, this is charge density here. And if you do that, then what you will get, apply this Gaussian's law, E ds, okay, equals to, okay, the body integration of volume, dV, okay, and this equal to this, right? So it's epsilon right? Okay. Left-hand side equal to this, also left-hand side equal to this, right? So these two equal to each other. And here importantly, then you will see, okay, because Gaussian's law, because Coulomb's law are satisfied at any given surface, right? Any given surface, any given area. So the only way that this equation can satisfy all areas and all surface is that these two equal to each other at every place, right? At every place. You can think about it, okay, if you satisfy in this place but not the other place, then you can simply include that smaller space into this integration, right? If you satisfy in this space but not here, then what you can do is that you can include this, okay, and form a new volume, and then you will see it will violate this. So the only way that this can satisfy every surface, every area, is that in every place you have the divergence of electrical field equal to epsilon rho. Okay, so that's the Gaussian's law. And then here, the D here, okay, we'll introduce this definition a little bit later, okay, but here the charge, rho meaning the density of charge, okay, density of charge. Any questions here? Okay, no. Then we will quickly say about the second equation, and then I will let you guys go. Okay. So the first equation is that the Gaussian's law here. Okay, it tells you that the relationship between the source, which is a charge, and your electrical field, right? So if you look at magnetic field of Gaussian's field, Gaussian's law of magnetic field, what does it tell you? It probably tells you that there's no source, right, to generate your electrical field. You can't have a north pole by itself. Right, you can't have a north pole and then it do this. Okay, if you have this, then at the position of north pole, it will violate this divergence of magnetic field will not be zero. Okay, will not be zero. So that's why, okay, when you have a magnet, okay, always have north and south. And then I think the magnetic line goes like this, outside the magnet, and inside, okay, has to go like this. So always complete the loops, okay, complete the loop. And okay, if you ask why, okay, why is it this way? There are several levels of answers here. The first is that where does the magnetic field really come from, right? So far, the magnetic field that we observe classically, okay, not quantum mechanically, classically, come from the, okay, inside, right? There's molecules, atoms, and then the electron actually circulate around the molecule, right? Circulate around the nuclear. Circulate around the nuclear. Then what you can see is that this actually give you a current, okay, which is a loop, right, in a loop, a little bit current. Then by one of the other rule, okay, you can see that this will actually give you magnetic field. Okay, it goes like this. Okay, and this type of source, okay, naturally give you a north pole and then a south pole, okay, in a very small way, right? So fundamentally, you have north pole and south pole. And then the magnet, what it does is that all the molecules, all the atoms, they are aligned so that the north pole pointing one direction, south pole pointing the others, right? If you're not magnetic, then, well, if a object doesn't have a magnetic field, then inside it's actually random, right? It's randomly so that they cancel each other, okay? But do we know for sure that you won't have magnetic monopole? Okay, magnetic monopole meaning that a north pole or a south pole by itself. The question is, we don't know, right? You can't rule it out completely just because you haven't seen it, right? So there are actually still researchers. So what people have found so far is that under okay, what condition, this condition, that condition, there's no magnetic monopole, right? It's like people do experiment and then they don't see it, then there's no, right? But then people now are actually trying to, do experiment in very extreme conditions, and then see, okay, whether you can, create, magnetic monopole, even though if they're not stable, right? And this kind of experiment is, somebody will call it meaningless, but I think it's meaningful in some way, right? Because if you think about it, that the atoms, right, they're a form of electron and nuclear. But what's in the nuclear? It's quarks, right? And how do you know it? Quark actually can be stable by itself. There are always at least 3 quarks together and then give you, spins and all those things. And what you actually do is you bump a nuclear with another nuclear, right? You make them collide, and then they become, unstable, and then they decay, okay, in a, very complicated way, so that it's possible, okay, it's totally possible that if you create certain experimental condition that somehow can give you a magnetic monopole, even it's not stable, okay. But then, of course, before you jump into any of this crazy experiment, you should actually at least know, okay, in the theoretically, okay, what situation will not give you a magnetic monopole, okay, and then so you don't look randomly. And there's some higher level of argument, for example, the symmetry argument, why they shouldn't exist, and all those. And then those are the theoretical physics side, and then I'm not expert in those. But anyway, this is kind of interesting. Okay, and then I will stop here. In the next class, we'll go with these two equations. Okay, and then also derive the wave equation for light, and then the speed of light, and then we can then kind of continue, okay, with the light and matter interaction part. Okay. Thank you guys.